Good morning, everyone. My name is Kim Nusser. I'm the marketing manager at Datacolor. I'd like to introduce to you Rick Mertens. Rick is an applications manager at Datacolor, and he has over 30 years of experience in this industry. So, Rick, turn it over to you.
Thank you, Kim. Hello, everybody. Greetings from Belgium. We will talk today about some of the matching techniques in the plastic industry. You will have the possibility to raise your hand. If you look at the GoToWebinar status bar or menu bar, you have an option to raise your hand where you can type in some questions. And at the end of the webinar, we will collect the questions and we will go through the questions one by one. The webinar today is going to last around 30 minutes and we will mainly focus on translucent matching techniques. So as a plastics producer, when using color matching software and using color measurement equipment, we would like to give you the possibility to enable better first shot matching. Color matching equipment is expensive, so it's quite important that you get the best out of your color matching equipment. And to do that, Datacolor is investing a lot of time and money in research. The research that we are doing is mainly going to two areas. The first area, we want to work on improved calibration of the pigments. We want to capture how pigments are behaving when we mix them together in polymers with or without additives. So a proper calculation and calibration of the pigments that you use in your daily life is quite important to achieve good color matching results. We also want to ensure that the matching algorithms that we use in our software are using the right balance between what you are using in practice. So we will talk a little bit about the different samples that you will use for matching, and we will talk about the different techniques to measure those colors. We can do that in reflectance mode and in transmission mode, and we will go deeper into details about that. The challenge when doing color matching is to capture and to try to reproduce colors that you receive from your customers. And when we look at such a sample, when we look at a plastic sample, then you see at the picture at the bottom of the screen that there is quite a challenge here. We have light which is falling on an object. Some of the light is mirrored back, and that's what we call specular reflection. Some of the light is absorbed by pigment particles. Some of the light is going through the plastic sample, and that's what we call transmission. Some of the light is scattered back by the pigments, and that's the color that we see. So there is a lot going on when we look how light is behaving on plastic samples. The challenge that we face with color matching software is to capture that behavior and to try to translate that in our algorithms. So let's look at some of the applications that we can use using plastics. If you look at the top pictures of the slide, what we have done here, we have put an LED box with LED illumination shining upwards, and on top of the LEDs we place some plastic samples, and you can see the LEDs still in some of the shapes that we are presenting here. In the middle of the screen we are showing an opaque plastic sample. You cannot see the individual LEDs anymore. That means that the sample, the plastic sample, is completely opaque. When we are dealing with opaque samples, the color matching is not that difficult. It's an application that is existing for many years and has proven reliability in color formulation. On the other side, we also have transparent plastic samples, and you can see here on the left-hand side an example of this, where you can still see the individual LEDs shining through the plastic sample. And then you have the translucent samples where light gets scattered while passing through the sample. You can still see the individual LED illuminations, but not so clear as with transparent samples. So in plastic industry, we are facing with the three kinds of samples. Opaque one, completely opaque, translucent samples, and the complete transparent samples. For opaque samples, we use matching algorithms, and these matching algorithms are based on the Kubalka-Munk theory. It's a theory that was developed in the 1930s, a very old technology where we basically say that every pigment is absorbing some light and every pigment is scattering some light. So basically, Kubalka-Munk says we need to calculate the absorbance of a pigment and we need to calculate the scatter of a pigment. Once we have absorbance and scatter, we can calculate the behavior of pigments and we can use this to predict opaque colors. This is what we call K and S values, K for absorption, S for scatter, Kubalka-Munk. When we look at transparent samples, it's also a quite simple theory that we are using. The light is going through the sample and is reflected by the support that you put on the background of the sample. So there the absorbance is coming from the pigments and the scatter is coming from the substrate that we use in the background. Also there the color matching theory is known for years, also known as Kubalka-Munk single constant theory. And we can use this both in reflectance and in transmission. In reflectance, we put a white background on the back of the sample when we measure with a spectrophotometer. When we measure in transmission, we will put the sample inside the spectrophotometer and we are looking at the light which is going through the sample. For translucent samples, it's more difficult because their light is going through the sample. So we have both transmission components, but also absorbance and scatter. In the past, many years ago, we used the Kubalka-Munk theory to calculate the behavior of translucent plastic samples. So we calculated absorbance and scatter. But in practice, it turned out quickly that Kubalka-Munk is not the right theory to take into account the behavior of light when dealing with translucent plastic samples. Kubalka-Munk had many limitations in that field, so years ago Datacolor developed the combined method, which is taking more into account the parameters that are playing with translucent plastic samples. For color matching, it is quite important that we simulate how you are looking at plastic samples. So opaque, no issue. We don't take into account the substrate. All the light is reflected back. No light is going through. Transparent samples, also no issue. We can measure that with a transmission spectrophotometer, and we can look at the light going through the samples. But for translucent plastic samples, we basically have two possibilities. The first possibility is by using a spectrophotometer and by measuring the samples over white background and over black background. If we compare the two measurements, then we can calculate how opaque or how translucent the sample is. So we compare the over white measurement with the over black measurement. That's one method. For applications where you go from transparent to fully opaque samples, many people are looking at samples by putting them on a white background and by holding the sample in the air and looking at the light passing through the sample. So in that process, the eye is doing a reflectance measurement by putting the sample on a white background and is doing a transmission measurement by holding the sample in the air and to look through the light passing through the sample. So if we would like to simulate this process, we will have to measure both in reflectance and in transmission. So for these applications, we will put the plastic sample behind a white background, and we will put the sample in the transmission port of the spectrophotometer to look at the light going through the sample. So the best approach for these applications is to simulate the visual process and combining the white background measurement with a measurement in transmission. So in Match Pigment, for users, it is quite complicated to know the best way how they should calibrate their pigments and their polymers. And we wanted to make it easier for customers and leaving the choice with the software based on the measurements that you are loading to the system. In the previous slide, we explained the two different methods for translucent matching. One, measuring over white and measuring over black and calculate the opacity of the sample. And the second method by measuring over white and measuring in transmission to look at the light going through the sample. So as explained briefly in the previous slide, there are different ways to do this calculation. And by introducing the smart calibrator in the software and by introducing some known formulas, the software will automatically use the best method to calculate the behavior of these particular pigments. So the benefit for the user is that if we have a proper calibration of the pigments, we can also benefit from superior first shot matching. Without a proper calibration and calculation of the pigment behavior in the polymers, it is not good to have a good first shot result. So how do we do this? We introduced a Smart Calibrator in Match Pigment version 3.0, and what we do is we load a few known formulas into the software. Known formulas with a known pigment combination in a certain polymer. And how many samples are needed? We recommend between 3 and 10 different known formulas going through the spectrum. Okay, with 10 colors we cannot cover the complete spectrum, but we recommend to have a yellow, red, green, orange, blue, black color. Based on these known formulas, the computer will calibrate your pigments by using all the available methods in the software. So the software will go through an iteration process. The software will try to match all these known formulas with method number 1, and maybe that's Kubelka-Munk, the pairs method. Then it will try the same thing with the new method, which we call the combine method. And in the combine method, it will try different parameters based on different optimizers that we use to calculate the behavior. So when we look at all the results from all the different methods, we can look at the method which is giving the smallest color difference, the smallest delta E for the known formulas. And that's the method that we will use to calculate all remaining pigments and polymers in this colorant set. So simply based on a few known formulas, we determine what is the best method to calibrate the colorant set. The best method is the method which is giving us the lowest delta E compared to the known formulas with a good contrast ratio prediction, hiding power prediction. At the same time, we optimized all the algorithms to make sure that all the variables are automatically calculated. When we talk about the combine method, we are no longer talking about simply absorbance and scatter of light. We are talking about a lot more variables. And these variables are determined of the two measurements, a measurement over white background and a measurement over black background, or a measurement in transmission. So by using these measurement data, we calculate all different variables, such as the film thickness, the specular value, the internal reflectance, and so on. And also in the software, we will automatically use and select the best mixtures. When you use color matching equipment, you need to make mixtures of all your pigments. Mixtures with white and black, without white, all in your polymer. We are recommending between 4, 5 mixtures to 10, 11, 12 mixtures, depending on the application. We are recommending mixtures with white, 1 or 2 mixtures with black, and mixtures without white and without black. By introducing all these mixtures in the software will do some checking, and he will automatically disable the mixtures which the software is thinking are not necessary to do a proper calibration. So when we suspect that a mixture is bad, or when we suspect that mixtures are not valid to do a proper calibration, we will automatically disable these mixtures. Once the process is done, the software will return us the calibration delta E's to make so that we can check how good or how bad we could calculate the behavior of each pigment in the polymer. What is the result of all this? When we match a color, and in this example we tried to measure a translucent yellow color with a contrast ratio of around 97.5, which you see here on the top corner, and with a film thickness of 0.9 millimeters. So when we measure the color, in this example, we measured the color over white background and over black background, not in transmission mode. Computer has calculated the hiding power of 97.5, and we introduced some tolerances, some freedom for the computer, and asked the computer to match between contrast ratio of 95 and 99. We selected in this example 43 pigments, and we asked the computer to match the color with a film thickness of 0.9 millimeter. This is the formula that the computer returned us. This was the original known formula. So as you can see, out of 43 pigments, there are a lot of possible combinations. The computer in this case calculated this pigment combination as first formula. So for a user, it's quite handy to make sure that we use the right pigments to match a certain colors if these pigments are introduced in the color system. And if you compare the known concentrations with the concentrations we calculated, you will see there is a difference, but the most important thing is the pigments are found back in the right ratio with a good theoretical delta E and with a contrast ratio which is close to the target contrast ratio that we asked for color matching. So this is an example to show you how we can match to known colors or unknown colors and making sure that we are using the right pigment combination, taking into account both the contrast ratio, film thickness and color of polymer and all other ingredients. This is a big step forward compared to where we were a couple of years ago, where the algorithms were not that much advanced and where it was quite difficult to make sure that the right pigment combination was used to match color. For matching applications, we also worked a lot and spent a lot of research on changing the current matching algorithms. So the benefit for the users is again making sure that the first shot matching results will be better compared to older software packages. So one of the examples what we have done is we introduced ROL and T matching. ROL means we measure a plastic sample over white background and we measure the same plastic sample inside the spectrophotometer and we are measuring the transmission value. So we are looking at the light going through the sample. To simulate the process that many customers are doing in their laboratories when they hold the plastic sample in the air and when they see if the color matching result is showing the same effect when the light is going through the sample. So the only way to properly simulate this application is to measure both in reflectance and transmission. Also, this technique is existing for many years, but especially the last year, Datacolor invested a lot of R&D in this to make sure that we find the proper balance between the matching that we do of the color over white background, the ROL measurement, and the matching that we do in transmission mode. So in the past, we did not pay enough attention to the result in transmission mode. Changed our algorithm so that we can scale how important transmission results are when matching a plastic sample. And here in this example, we are so measuring a green color. And you see on the left-hand side the measurement of the green color over a white background. And on the right-hand side, the same plastic sample, but then as a transmission measurement. We did the calculation of, and we let the computer free to calculate a recipe, and it's showing us the color difference over white background, the ROL measurement, which is giving us a delta E of 1.32. And at the same time, it's also showing us the transmission result. And here you can see a delta E of 0.53. So with this example, even if we don't have a perfect delta E of 0.00, we are balancing the result between what we can get over white background and what we can get in transmission. This is much better than ensuring that we have a delta E of maybe 0.0 in reflectance mode, but maybe a totally different color in transmission mode. If you look at the reflectance curve and the transmission curve, you can see that we are following exactly the same shape as the target color, both in reflectance and transmission. So with this new method, we are much more confident that we start from the right pigment combination when using and when matching using the reflectance and transmission mode. So this is a step forward in the matching process from transparent to opaque samples and all the way in between those two limits. In Match Pigment, we also introduced a technology called Smart Match, and we will have a separate webinar in the future concerning Smart Match technology, but I just want to take the opportunity to briefly explain what Smart Match is. In plastic laboratories, people develop new colors every day, and these new colors that they produce are good reference for the computer. In many cases, people use these colors for searching. When I have to produce a new color, I will first search in my library to search for the closest color. With Smart Match technology, we go a step further. Instead of looking at the closest color, we will analyze the pigment behavior. So what we will do is we will group all pigment combinations together, and every time you make a color in your laboratory and you store this color recipe in your color matching software, we will store the pigment combination, the film thickness that was used, the polymer that was used, and we are storing this as a smart match point. Now, if we have to match a new color, we will not search for the closest color in the neighborhood. No, we will look for a color which can be made with exactly the same pigment combination. Since we store the pigment combination, we know how these pigments are behaving in practice in that particular polymer. And we are using this experience to correct the match prediction algorithms. So the benefit for the user is that with smart match technology, you are using experience from your trials that you make in the laboratory, and you will use this experience when matching new colors. It's much more powerful than the search technology that we were using in the past. So as a conclusion, what I would like to mention about matching translucent plastic samples is proper calibration of the colorant set is very important. There are different methods that exist today to calibrate your pigments. We have chosen to create a smart calibrator that will try all the different methods to calibrate a pigment set and to choose the best method to make sure that we can do a proper calibration of your pigments in the polymers that you are using. At the same time, for matching, beside the traditional processes like measurement over white background and measurement over black background, we also improved the technology for combining a measurement over white background and a measurement in transmission mode. That during the matching process, we are selecting the optimum pigments to have a good match both in reflectance and in transmission, so that the steps needed to reproduce colors is less compared than the past. And finally, by using smart match technology, by using experiences of the past, you can have better first shot matching predictions because we are calculating the behavior of pigment combinations when they are used in a polymer. So I'm coming to the end of the webinar where I explained a little bit what is new in plastic color matching, plastic translucent matching. And I would like to ask if there are questions, if you would like to have more explanation about one of the topics that were mentioned during the webinar. So Kim, I will hand over to you and maybe you can go through the questions.
Okay, Rick, at this point we don't have any questions, so I'll ask that any attendees who may have questions go to the questions section on the GoToWebinar control panel and submit them, and we'll wait another minute to see what we receive.
Thank you, Kim.
Okay, we do have a question. Newman is asking, can we store smart match point with ROLT measurement of the batch?
Yes, we can. So smart match points can be stored both reflectance over light, reflectance over dark mode, and reflectance over light and transmission mode. So during the last 2 years, we also improved the algorithms for smart match to take into account the measurements over dark background for both reflectance and transmission mode.
Okay, again, if there are any questions, please use the question section on the GoToWebinar panel to submit your question, and we'll wait another moment.
Kim, it's also possible to email questions.
Yes, you can email questions to webinars@datacolor.com, and we can pass them on to Rick to get an answer for you. Okay, we have another question. The formulas within the colorant set are not used also as smart match points?
They can be, they don't have to be. So my recommendation is if you have known formulas, you can also use them as smart match formulas, but it's not an obligation. The only thing is the more information we have in the smart match library, the more accurate the matching will become. But typically the known formulas that we are doing during the calibration, the only purpose of these known formulas is to make sure that we use the right technique to calibrate the pigment behavior. So choosing between Kudelka-Munk and the combined method, and within the combined method, making sure that we are using the right techniques to have the best variables to match the known formulas.
Okay, that appears to be all the questions today, Rick.
Okay, then I would like to thank you for your attention. And please, if you have more questions, do not hesitate to write us an email and we will answer as soon as we can. Thanks a lot for your attention and have a nice day. Bye.